as Colin said, my talk's going to carry on a little bit from where Tom Fuller left off. I'm going to try and answer some of the questions that were raised in his talk. In particular, there was the question of, should you have one model that does everything, or should you think about separate models for separate timescales? And then a question that arose in the question answer session was, could you ever get a physics-based model like DFN into a battery management system given the reduced processing power? So I'm going to try and address both those issues. Through doing reduced order models, so reducing the complexity of a continuum model through a systematic asymptotic analysis. And I'll try and give you an idea of the advantages of doing it systematically through asymptotic analysis. In order to reduce a model, I have to give you an idea of where I'm going to start from. So what's sort of gold standard as far as I'm concerned. And for a general talk, normally I'd take a long time doing this. In this audience, I hope that most people are familiar with the equations I'm going to write up. So I'm going to go through that quite quickly. I have to say my talk is front loaded with equations as well. There are a lot of equations on the first two slides. There are almost no equations after that. So bear with me for the first two slides. So the situation we've got, I've drawn here a single pouch cell. I have an anode and a cathode, separator, and two current collectors. And we've had models at the level of atomistics and DFT. I'm not one of those people. I'm starting at the continuum level. So the sort of equations I'm going to write down are in the anode. For example, I've got electric current with a potential with Ohm's law, and then I've got some lithium intercalation. So Ca is the concentration of the lithium atoms. And I've just written down diffusion here. You could do something more complicated if you want. In particular, the diffusion coefficient could be a function of the concentration. In the electrolyte, you're going to solve equations for the positive ion Cp, lithium, and the negative cation, concentration Cn. And I've got conservation equations for those with fluxes given by the usual expressions. And again, the diffusivity here, which is related to the conductivity in the electrolyte, could be a function of the concentration. On the interface that you have, you've got no electrons coming out there, so the electronic current is zero. And then whatever lithium comes out of the electrolyte must go into the active material or vice versa. And so that's the continuity of fluxes there. And the flux is given by this expression QA that I'll come back to in a minute. I need to give you one equation for phi that I haven't given you yet. Normally that's charge neutrality. So I impose that the concentration of positive ions is the same as that of negative ions. And then you can take linear combinations of the equations to reduce it to a single diffusion equation for the concentration of either species. And then the divergence of the ionic current is equal to zero. And the boundary conditions transform appropriately. Then the final ingredient in the model is to tell you what the Q is, and that's given by the Butler-Volmer relation, which I've written it down. It's a bit horrible, but everybody is familiar with it in this audience. And the U there is the equilibrium or open circuit potential, which is a function of both the concentration of the positive ion in the electrolyte and the concentration in the anode. So that is, in some sense, the gold standard. That's the model that I'm going to start with and try and reduce asymptotically. And the first step in that reduction is to go to a porous electrode theory by doing a homogenization. So you can do this by systematically, mathematically homogenizing such an equation. And what you end up with is this sort of system where I now have a set of equations to solve in the porous electrode, and therefore I solve both for the concentration in the electrolyte and for the electronic and the ionic current in the same region of space. And so psi here is the volume fraction of active material. What was a surface term has now become a volumetric term as the lithium comes out of the active material into the electrolyte or vice versa. And so you have source terms for both the ionic current and the electronic current and in the concentration C. A key parameter that comes out here is A, the surface area to unit volume. And in principle, if you do this homogenization, you could work out what the effective diffusion coefficient and conductivity of both the electrolyte and the active material, what they are as a function of the microscopic geometry, if you knew that geometry. And we heard yesterday about if you have degradation and that geometry is changing, what's the effect on those conductivities? And in principle, this procedure would allow you to do that. My feeling is that it's not going to make much difference, and the degradation would make a much bigger difference to this surface area per unit volume parameter there, A. So you solve this at every point in the three-dimensional cube there, and then I've still got the Q there, and I have to tell you what that is. So to do that, at every point you have to solve a microscopic problem, which is intercalation into a representative, what's known as a unit cell of the anode material. And here I've just written it as though it was linear diffusion, but you could do all sorts of things there. And the two models are coupled together through the flux Q. So that's a boundary condition on the local problem, and it's the volumetric source term in the macroscopic problem. So I'm going to call these, the microscopic problem is the cell problem that I solve for intercalation into the anode material. And what I'm going to call the macroscopic problem is the problem for the electrolyte, etc., that's on the scale of the whole cell. So that's the first step, and that's now porous electrode theory along the lines of the DFN model. Looks like I've done something a bit stupid there, in the sense that I started off with a three-dimensional model, and I've now turned it into a six-dimensional model, because I have a three-dimensional macroscopic equation, and at every point I have to solve a three-dimensional microscopic equation. But it turns out that those models are now much better conditioned than if you just solve the whole thing on the micro scale. In particular, the equation for the electrolyte, I can discretize that on a much coarser scale than I would use for the active material. So it still is, even though it's a six-dimensional problem, it's still easier to solve than the original problem. But one of the great advantages of this sort of model is that it's now ripe for further analysis. It's in a form that you can simplify it much further. That's one end of the scale. What's the other end of the scale? For things like battery management systems, you might write down an equivalent circuit model, which is a set of resistors and capacitors typically. So that's, you're now talking ordinary differential equations. So on the one hand, I have a six-dimensional partial differential equation. And at the other end of the scale, I have a zero-dimensional equation. So zero-dimensional means partial differential equation gives me an ordinary differential equation. And I want to try and use asymptotics to get from one to the other. So what sort of simplifications might we be able to do? Well, there's at least three timescales to consider. I've written three down here. One is the time that you take to charge or discharge your whole cell, your C rate. The second is the time it takes for lithium to diffuse in the electrolyte. Depends on the diffusion coefficient and on the length scale. And the third is the time it takes for lithium to diffuse in the electrode, in the active material. So diffusion coefficient is typically much smaller, but also the distance it has to go is much smaller. So that time scale can also be comparable. The other parameters that you have to consider, where there might be some room for simplification, is the different resistances. So when I'm thinking about my current collectors, typically a current collector is much more conductive than the cell itself. Otherwise, I would just, if I had tabs at the top of this diagram here, I would just follow the first path and short circuit. So you typically make the current collector very conductive, but it has the longer distance to go down to the bottom of the cell and across. And so you have to worry about what are the resistances of these two paths where I go much longer through the current collector. And that's another important parameter that's going to come up in the asymptotic analysis. So based on those simplifications or those parameters, you can end up with the following suite of models. So I'm not going to show you any equations for how you reduce these or for the model you get. I'm going to try and show you pictorially so that you sort of get the idea and the flavor of the sort of thing that you can do. And So in these models, I'm using geometry to show you what's the dimension of the equation that I'm having to solve. So a slab represents a three-dimensional equation, a plane or a sheet represents a two-dimensional equation, a line or a rod is a one-dimensional equation, and a point is a zero-dimensional equation. So by that, I mean an ordinary differential equation. So at the top left, I start with the complex 3 plus 3-dimensional porous electrode model. And as I move from left to right, I'm simplifying the macro scale. So by the time you get to the right-hand side, the macro scale is very simple. And as I move from top to bottom, I'm simplifying the micro scale. And so you can mix and match, and by simplifying each of those independently, you end up with this grid of possible models. And I'm just going to sort of show you by stepping from one to the other what simplification we're doing at each stage here. So this is the 3 plus 3 that I'm starting off with. If I go to the next one on the left, then this corresponds to taking the limit in which the aspect ratio of the cell is large. So typically these cells are the distance between the current collectors, it's much smaller than the lateral dimensions of the current collector. But the conductivity of the current collector is much higher than the cell. And if you take that limit, then you turn this three-dimensional model into an array of one-dimensional porous electrode models that are all coupled by the two-dimensional current collectors at the end. So you sort of you turn that three-dimensional model into a 2 plus 1-dimensional model. And it seems strange for a mathematician to say 2 plus 1 is not the same as 3, but in this case, it's true that you now don't have to worry about any lateral diffusion or connection between these one-dimensional models. They're only connected through the boundary conditions at the endpoints. And that is simpler to solve than solving the full 3D problem. This is such a natural thing to do that often you do this without even realizing you're making this assumption, and that it is an assumption that you can effectively solve these as one-dimensional problems. If the current collectors were even more conductive than that, then the potential would be uniform on the current collector, and then all these one-dimensional models would be the same. And so instead of having to solve a lot of them, I only have to solve one of them. I still have a two-dimensional problem to solve at the ends, because depending on where I place my tabs, the current distribution in the current collector is non-uniform, and I get a resistance from the current collector, and I can work out what it is by solving a single sort of decoupled two-dimensional problem. And that's quite a nice problem to solve, because that allows you to play with the geometry of the tabs and things like that in order to optimize, in some sense, the current collector in terms of its resistance and maybe its thermal properties. If you take the limit in which the current collector is even more conductive than that, then you don't have to worry about that resistance at all. And effectively, you've taken the current collector out of the problem now. And you just have a single representative, one-dimensional porous electrode model to solve. And then the final simplification on this row is to say that the time scale for diffusion in the electrolyte is much shorter than the time scale for discharge. And that means the electrolyte sorts itself out very quickly, so that you don't have to worry about solving for the electrolyte. Concentration is just uniform. And then instead of having a representative cell problem at every point in that one-dimensional thing, you just have one representative cell problem for the whole anode and one for the whole cathode. And that's the equivalent to effectively the single particle type of model. So that's the macro scale. What about if you start simplifying the micro scale? So the first thing that's usually done is that you take this complicated geometry and you reduce it to a collection of particles which are spherical. And you might have a distribution of particles, of spherical particles at each point in your cell. Then distribution is unimodal. You say, well, let me choose a representative size for each particle. And we've been doing some work on that to say, what's the right size to choose? Should you choose the average radius? Should you get the average area right? Should you get the average volume right? Should you choose the volume weighted average of the area? There are all sorts of things you can do, and depending on exactly what you want your model to reproduce, the different choices are appropriate. And then the final thing you can do on this microscale simplification is to assume that the diffusion in the active material, the solid state diffusion, is much quicker than the timescale for discharge if you're discharging slowly. And then the concentration in the active material is uniform as well, and you just have an ordinary differential equation to solve. So I'm representing that by a point here. So that sort of explains how you get to this hierarchy. Let me pick out one or two models here. So this is where DFN would sit in this. You have a single one-dimensional problem, and at each point in space, you're solving a radial problem for a representative spherical particle. So that's the pseudo 2D DFN model. If I go to the right, then this is where a single particle model fits in. I have a single spherical particle representative in the anode and a single representative spherical particle in the cathode. And if I go right down to the bottom right here, then I've got ordinary differential equations everywhere. I have a single ordinary differential equation for the anode and a single ordinary differential equation for the cathode. And you're getting to the stage of sort of equivalent circuits here, at least in terms of complexity. You can, of course, do these asymptotic limits in different orders. So I talked about taking the high conductivity in the current collector first and then taking high conductivity in the electrolyte. You can do those in a different order, or you can also do the microscale ones in a different order. So instead of going to a single particle and then saying it's fast diffusion in the active material, I could say, well, I'm still keeping a collection of many particles. So I've got distribution of particle sizes, but diffusion is fast so that I'm only solving a collection of ordinary differential equations for them. And then if you do it the other way and you say, I'm gonna take the limit in which the electrolyte is very conductive, or timescale for diffusion is small by comparison to discharge time, before I take the high current limit, then instead of getting a sequence of DFN models all coupled by the boundary conditions, you would get a sequence of single particle models, or a grid of single particle models, all coupled through the two-dimensional current collectors at the end. And of course, you can do that and then say, well, the current collector is a little bit more conductive even than that, and then you would get effectively a single particle model with an in-series resistance that you can calculate due to the two-dimensional current collector. So let me just highlight a couple of these things that I'm going to show you some simulations of later. So this is, on the right, I have the single particle model, and that's an asymptotic limit of the model on the left, which is the DFN model with the two-dimensional in-series current collector. And the advantage of doing asymptotic analysis to reduce one of these to the other is that, well, first of all, you know for which values of the parameters your reduced model is valid. You know what limit it is that you're actually taking. And the second thing is that you can choose to keep not just the first term in that expansion, but you can generate higher order terms in that expansion and keep those as well. And that allows you to generate models which move towards the fidelity of the model on the left, but with the complexity of the model on the right. And we've looked at such a model. We call it the SPME, for single particle model with electrolyte. And the words here is on this slide explains things I've already said. It basically allows you to push the single particle model to higher C rates, and it captures some of the variation in concentration that you would get in the electrolyte. The graph at the top right here shows you a comparison between the single particle model, the SPME, and the full DFN for 3 different charge rates. And the take-home message is that SPME is a little bit more complicated to solve than SPM, but it's the same order of magnitude, maybe twice as slow. But it's at least an order of magnitude faster than solving DFN. Here it's nearly 15 times, say. And you lose a little bit of accuracy over DFN, but you gain accuracy over SPM. So it's a model that is more accurate than SPM, but not so complicated to solve as DFN. The other case that I just want to highlight, I've mentioned this already, but I'm going to show you some simulations of this 2+1D pouch cell model, in particular the model in the middle here, where you get a series of one-dimensional porous electrode models coupled by two-dimensional current collectors. So I'll show you some simulations of that a little bit later on. And it just shows you exactly what parameters balance you're choosing in order to get the model in the middle there, and what does high conductivity mean and what does very high conductivity mean. And it's to do with those the current paths that I showed you earlier. So Lx is the thickness of the cell between the current collectors, and Lz is the lateral dimension. Right, so I want to have time to talk about software. So again, sort of following on from Tom Fuller's talk, he said that can we make our models more accessible to battery developers? And so we've been very keen that we develop these models, but we also implement them in a way that makes it easy for people to use them. And the software system that we've been creating is called PyBAM, for Python Battery Mathematical Modeling. And it's really, it's a framework for building models. So it's not just, we're not just putting our models in and then off you go and you simulate with them. The idea is that it's very easy for people to add their own models to it, and it's very modular. It's sort of plug and play. So you choose, if you have a new model for your active material, it just slots in there, and you can use existing models for the electrolyte and everything else. So it's very easy to get up and running, and I'll show you that you can go from not having it installed to having a simulation running in about 2 minutes. I'll try and show you that at the end. But the idea is that it's a community resource, and we hope to have build a community of people that add their models to it, so that you can basically, as I say, plug and play. But many of the standard models are already implemented and they're easy to use. And these are the main architects. There are other people who have been involved at later stages, but these are the people who are really the core PyBAM team. So at that stage, I want to switch and see if I can do some live PyBAM demonstrations. So let me show you. You can obviously run this thing in scripts, but I've just got this up in a Jupyter notebook so that it's easy to demonstrate. And this just shows you how many lines of code you need to run a standard DFN model. So all I have to do is I import PyBAM. I define my model to be the standard PyBAM lithium-ion DFN. I define a simulation that's now going to use that model. And because I'm not changing any of the defaults, all I have to do now is do sim_solve. And there it solved it. And now if I plot it, you get the standard thing. This is the variables that the standard plot shows you. So negative particle, the surface concentration as a function of distance through the electrode, the electrolyte concentration, positive particle surface concentration, the current, the terminal voltage, the potential in the positive electrode, the potential in the electrolyte, and the potential in the negative electrode. So all these ones are functions of space, distance through the electrode, and this is just a function of time. And then you can click through this. I could drag it, but I think the delay on the presentation might not work so well. So I'm just going to click through to various times and just shows you that solved DFN in that time. There are lots of other things you could choose to plot. So I just plotted the default there. I could, here I've chosen terminal voltage, electrolyte concentration, electrolyte current density, which wasn't shown before. You choose to plot those and you can see how these vary through this discharge. The standard thing is a 1C discharge. So that notebook is just designed to show you that it takes 3 or 4 lines of code to get you up and running and solving DFN. let me show you something a bit more interesting. We wanted to make sure that it was very easy to compare models in PyBAM. In particular, because we were developing asymptotic reductions of DFN, we wanted to see how good was that reduction. Could we quantify what the error was? And so we thought it would be very useful to just be able to do that all within PyBAM. So here, let me import into this new notebook. I'm going to define now three models. One is the single particle model, one is the single particle model with electrolyte, our asymptotic reduction, and one is the standard DFN. I'm switching the solver to the fast mode of Casati, and then I'm just going to solve for each model in that suite of three different models. Let me show you how quickly it did that. So that solved DFN in 0.1 seconds. It solved single particle model in 0.01 and 0.018, and it solved the one with electrolyte a little bit quicker. That's a bit weird because the electrolyte one should be harder, and I think it all depends on what else is going on my machine. So let me run that again. That's a bit more like it. So single particle model was then in 3 milliseconds. Single particle model with electrolyte 7 milliseconds. DFN in 0.1 seconds. Usually it's a little bit quicker on DFN as well. Let me show you what the results look like. So here it's plotting all three. Let me come to the terminal voltage as a function of time here. So you can see the single particle model is in red, the DFN is in black, and our single particle model with electrolyte is in blue. So you can see at this discharge rate, which again is 1C, there's an error in the single particle model in the terminal voltage, but that's been corrected with the single particle model with electrolyte. And if I just flick to some times here so that you see some intermediate results, you can see, for example, if you look at the electrolyte concentration, the single particle model has that uniform because it has no spatial variation, but the SPME, even though it's the same sort of complexity, it has the correction term, and therefore it does see some variation in the electrolyte concentration. And at this time, it's got that pretty well matched. If I go to later times, you start to see some error between the single particle model and the full DFN, as you would expect. But it's SPME is doing a lot better than SPM. So that shows you the default things. Let me just quickly show you how easy it is to change some things in if you don't want to use the defaults. So I already showed you that if you want to switch to fast mode in the solver, you define your solver and you pass that to the simulation. If you want to change the number of grid points, so that this is the default number of grid points, 20 in each of the macroscopic dimensions, 10 in the current collectors, and 10 in each of the representative particles. If you want to change that, it's very easy. You just define a vector that tells how many points you want in each region, and then you pass to your simulation the new number of points in each variable and solve. So very easy to change how many points or the fidelity of the discretization. If you want to change the C rate, you just pass that as a parameter. C rate is equal to 2, would solve it with a C rate of 2. If you want to change the default parameter values, I think the default parameter values are taken from dual foil. But there are various other ones that you can put in for different chemistries. So you basically define your chemistry. You can define it manually, or you can define it to be one of the other sets that's already in there, and then you just pass that in as your parameter value. Off you go and solve. If you want to use most of an existing parameter set, but you don't like one of the values, then you can just individually change one parameter value to be whatever you want it to be, and pass it in and then solve. And then finally, before I will show you some more examples, I want to show you some part of this is an advert to try and encourage people to come and contribute to this software. So how would you try and write a new model? you basically define a new model, you define your parameters, you define your variables, and then you write down your equations, and you write them almost at a symbolic level. So it's built around conservation equations and fluxes. So you basically define fluxes by using the gradient operator. You define the right-hand side of your equations by typically it involves things like divergences. And then the equations are always in the form of d variable by dt is equal to right-hand side. So that's why I've called this right-hand side dc by dt, because you pass the model right-hand side, whatever the value of your time derivative would be. And that's it. That's a model that then would solve the heat equation for me. So if you're adding a model to PyBAM, you don't have to worry about spatial discretization or numerical solving or anything like that. You just pass it effectively, you pass it the equations. Right, let me show you. I've got 3 other quick notebooks to show you. I promised to show you the 2+1D pouch cell. So let me show you that one working. So this is I now have to pass some options to the model. So I have to tell it that I'm doing potential pair. That's the potential in the 2 current collectors is different. It's a 2-dimensional problem, and I'm doing the thermal problem, which is integrated across the cell. Thermal variation across this cell is very minimal. In order to get this to solve live, I'm just going to reduce the number of variables, the number of points in each variable to 5 rather than the standard 10 or 20. I pass it the parameter values. So I want to do this for 2 electrode thicknesses. So instead of having to compile the model each time, I'm just going to define the current collector thicknesses, sorry, as an input that I can pass afterwards without needing to recompile. So then I define my simulation, and now in order to solve it, I'm going to pass these 2 values of the current collector thickness at 25 microns as inputs. I'm going to solve it, and it takes about 3 or 4 seconds. There you go. And I've just plotted the terminal voltage and the average cell temperature. And this slider just moves you to wherever you are on that. You see, this is again, I think a 1C discharge, and the volume average cell temperature is going up by a few degrees. I think we changed some of the connectivities to make something interesting happen here. Let's have a look at some 2D variables. So 2D plotting, you have to do a little bit of custom stuff at the moment, which is what that was for. So this is what the average cell temperature looks like during the evolution. So this is now solving a set, I think it's a 5x5 grid of single particle models. What were we running? SPME. So we're doing SPME, a 5x5 grid of SPME models here. Fully thermally coupled. We can have a look at what's happening with the current. Current collectors are at the top here, so that's why there's more currents coming in at the top. That's why there's more current there. Now, something interesting happens between 1500 and 1800, and suddenly the depletion is such that the preferential, the current path goes from the top to the bottom suddenly, and then eventually comes back to the top again. Of course, the differences are small here. If we want to solve that at a different thickness, I just give it different inputs and solve it again. I don't have to compile it again. So that's very useful, not so much for notebooks, but if you want to do a script, for example, that solves at different thicknesses and compares, then that's the right way to do it. Now you can plot. So this time I reduce the thickness of the current collector. And sorry, did we reduce or did we increase? What did I do last time? 25. So I reduced the thickness of the current collector so that its conductivity is lower, so its conductance is lower, and therefore I get much stronger temperature variation. These are just to show you the sort of thing that can happen. Right, the other thing we're quite excited about is experimental protocols that we've got built into PyBAM to make it very easy to simulate an experimental protocol. So for example, this is constant charge, constant current, constant voltage. And you basically write it almost in the way that you would say it. So this, you define an experiment to discharge at C/10 for 10 hours or until 3.3 volts, rest for 1 hour, charge, etc. And that is now, you can do it 3 times over. I'm going to pass that to a single particle model. I'm going to pass in, it's the same command I had before, but now with the model, I'm just passing in that experimental protocol. I solve it. And I can plot. And so you see, you have your current going in, you have your terminal voltage, and obviously all the other variables are available for you to investigate. There's Git as well. So here, discharge at C/10 for 1 hour, rest for 1 hour, and do that 20 times. It's the plotting that takes longer. There you go, and there you have the gradual drop off of the terminal voltage. You can also do drive cycles, something a bit more challenging. So this is with DFN now. It's the parameter set from Gen 2020 that was recently put in. I'm going to give it fast mode. It's the US06 drive cycle. And if I solve that, and plot, then you see that it managed to do that fairly well. I think that's my, can't see, I think that's my last thing. So let me go back to Keynote. So I said we are fast as well as flexible. So let me just give you some examples. So this is with the dual foil parameters, just to show you how quickly it solves DFN. And just for comparison, we happen to have this in console. We tried to arrange it so it was the similar number of states that it was solving for. And you can see that that fast mode does very well, absolutely beats console hands down. So not only is it easy to use, easy to set up and flexible, but it's also very fast. I should mention, we have a few different solvers in there, from the scikits DAE solver to IDA KLU to Casadi safe mode and fast mode. What's the difference between safe mode and fast mode? So fast mode, if you're charging hard, and fast mode might give you a negative concentration, and that could cause it to crash. Safe mode sort of integrates and checks to make sure that doesn't happen. If you're doing something like a drive cycle, you're safe, you can do a fast mode. If you're really pushing it hard and you might get to the state where concentrations were close to 0, then you want to do Casadi safe mode, which slows it down a little bit. Right, that brings me to my conclusion. So asymptotic analysis is a way to systematically reduce the complexity in a problem. It enables you to know exactly what approximation you're making and therefore in what parameter regime your reduced model will be valid. If you keep not just the leading term, but higher order terms in some asymptotic approximation, then that often gives you increased fidelity for minimal additional cost. The result is a suite of reduced models of different complexity and fidelity. And in this framework, both in PyBAM and in the asymptotic reduction, other effects can easily be built. We've already got thermal effects in that. We're looking at doing mechanical effects, chemical effects such as SEI or nonlinear electrolytes, concentrated electrolyte theory, all that can be built into the general framework. The final thing, so that is basically the end. I was going to show you how easy it is to get PyBAM up and running. So there's the, it's all on Git. You can download, there are lots of example notebooks and things that you can use there that sort of act as tutorials to teach you. But to install it, you can just pip install it.